Hello, today we are looking at functions as stories, and we can really get a lot of this from graphs. If you have a function, for example, like f of x equals x plus 2, it is difficult to maybe think about this as a graph, as it is, but for the purposes of putting it on a graph, quite often we just substitute f of x for y. So y equals x plus 2. It is a very easy way to graph functions. Just substitute y for f of x. All right? Knowing that, functions can tell us stories by examining them. Unfortunately, most of those stories do not begin with a long time ago in a galaxy far, far away. That would be pretty cool, but they're cool in their own right, I suppose. So, distance versus time. First of all, this is a very common way of writing a graph out. It's described as your y value, so in this case distance, okay, distance is my y, versus your x value, versus your time, your independent variable. Time is almost always going to go in the x because that is the independent variable. You cannot control time unless you happen to have a DeLorean and a flux capacitor. If you've got that, then, well, more power to you. So you've got distance, usually it's in some sort of measurement here. It could be in meters, it could be in kilometers. You've got time, which could be in minutes. Quite often it's in seconds. Whatever it may be, that's fine. What does this line tell us if this is our graph? Well, it looks linear, right? There's no change. So what is the slope here? It's pretty constant. So looking at this, what I would see is that I'm always increasing. So the distance away from the starting point down is always increasing. So you're always moving away from something. And the slope, if we look at a change from like here to here, we're able to look at that slope. If we have the exact equation for the function, it's easier to prove this, but it pretty much looks like the slope is equal, that I'm always going through the same quantity of change here. So it looks like I'm always moving away, and because it's linear, so the slope is constant, so that means I'm moving away at a constant speed. It's maybe not the most interesting story, but I would say that whatever we are graphing, if it were a car or a bike, the Millennium Falcon, whatever it may be, we are moving away from the starting point at a constant speed. All right, let's make it more interesting. How about this guy? Distance versus time. Again, same type of concept, but we see, whoa, all sorts of stuff going on here. So here, at the beginning, is kind of like I just had up here. I've got a period of constant movement. Okay, it's constantly moving away. Distance is increasing. And at about the same rate. So constant speed away. Okay, now what is going on here? Keep in mind this is distance and this is time. Time continues to advance. Is the distance away from the starting point changing? The distance is not changing. So you can picture it driving along and then you get to a point, maybe a stoplight, and you sit there. Time continues, but there is no movement. So this would indicate that there's some sort of stop and wait. Time continues along, but there's no change in distance. There's no movement going on. And here, what do we have now? In this third section, we've gotten movement away. Distance is increasing, so we do have some movement there. How does that compare to our first section? See how the slope kind of looks like it's a little bit higher? What do you think that means? It's a little bit lower here. So I have a lot more distance that is moved in a smaller amount of time. So in other words, you could say you've got really a greater speed. You're moving farther in a shorter amount of time. That's really all that speed is, right? Or velocity, if you want to be quite technical. Distance over time. If you want to be really technical, change in distance over change in time. Okay, let's continue our story. What's going on up here? In this fourth section, time continues, but there's no more movement. Oh, now what about there? In this fifth section, what's happening to the position, to the distance from the starting point? The distance is decreasing. So that means you basically are going in reverse, or you're returning back toward where you started. Because the distance from the starting point that we left way over here at the beginning of time, is decreasing. And what's going on here in this last section? You should be able to explain that one by yourself at this point. If not, rewind a little bit, do a quick recap. So again, this graph can just tell us a story of where an object is over time. Maybe this is what someone's car had done if you wanted to track position away from someone's home. There can also be other graphs that we can look at like this. Savings over time. So if you've got a little bit of money invested, we can maybe focus on this part over here. How quickly do you get more savings here at the beginning? Is it pretty gradual? Is it very quick? Look at the amount. So I'm increasing here a little bit over some time. Maybe about the same time. Here again, a gradual amount of increase. But if I look at that over here, at that same amount, excuse me, how much are we increasing? Whoa, or what about, whoa, right over here. Whoa. Okay, I'm eyeballing these a little bit, but still, the concept is the same. Where are you getting more money more quickly in your savings account? It's very gradual growth over here on the left, but on the right, we can see that the rate of change is higher. And you're getting more money more quickly. So even though there are no, well, I suppose there are some words, but there are not a lot of words in our graphs that we're looking at, if you look at them and you think about the relationship between your y and your x variables, you can make a story out of that that tells you some information about what is being graphed. It takes some interpretation, but it's a wonderful skill to have, and we'll be practicing that. So keep thinking about this, review if you need to, bring your questions, and I hope you have a great day.